Alrighty, good evening, everyone. It's 10:27 p.m. Saturday, July 5th. People are still popping off some fireworks today. Okay, yeah, my apologies. My earbuds were not working. Sorry about that. People are still popping off fireworks today after the 4th of July yesterday, probably remaining. So hopefully you won't hear that in the video, but we'll see. We're going to continue on. Could do 3 today or maybe 4, we'll see. Alright. Given an integer array nums, find a subarray that has the largest product and return the product. The test cases are generated so that the answer will fit in the 32-bit integer. Ooh, it's a decision tree here. Oh, subarray. Okay. I see. It's probably they warned you saying like, hey, yes, it should be able to fit inside the thing. What's up, bro? Okay, so I'm pretty sure my choice is like you'll take like hash of I or I minus 1, and then you can either multiply it by this or keep it as is. Max. Don't give me that look. Okay, I'm gonna say I don't know, index. Index is a good number, I guess. If index is less than 0, then we I guess return, I don't know, just return 0. Yeah. If cache of index, or sorry, I guess if index not in cache, then we're going to basically do our solution, and then we're going to return cache of index. Okay. So I'm going to say cache of index is going to equal to solution. Okay, so this is where our recursive relation is going to come into play. So my thought for the recursive relation is you have 3 choices. Either you take the previous one as is, you take the new one as is by itself, or you take the old times the new. So 3-way decision tree. I'm going to say previous equals dp of index minus 1. current equals nums of index. I'm going to say solution equals max of previous times current, or max of previous and current. And then I'm going to say that this equals solution, and then I'm going to return dp of length of nums minus 1. Alright, let's see if that actually runs or not. Runtime error, because I didn't write an equals sign. Did not run. Dude, if I get a DP question like on an interview, I'm actually fried, because like, I mean, I eventually get the question right, but it takes me way too long. Like, six? Why? I guess maybe instead of doing that, we need to oh wait, oops. I guess it doesn't matter, it's still working, but I just like having that anyways. Okay, we get 2, then we get 6, then we get 6, and we get 4. Ah, fuck. I see the exact problem. Crap. Crap. You have to have some sort of checker, basically it's like, that this is a contiguous. Ah, crap. I didn't even think about that. Ah, crap. Tell me, what's the decision tree on that? Sorry, just checking something on my arm. Okay. It's probably like a situation where it's like you can take or you cannot take. See, the thing that's tricky is like the whole thing changes. Like you could have it be like this is 6, this is the greatest, and you have like 4 here, and then you have like 8 here, and then like boom, like you cooked. Okay. Damn. I suck at these problems, man. Oh, then. Yeah. What? Whoa. Hold up. Min-max. I'm getting a little confused by this. We maintain both a minimum and a maximum product values and update them. I'm introducing a new element. What's the previous min product? I don't think I'm understanding the min product right, because it's like, for example, in this situation here, my min product would just be like negative. It'd be a huge negative number. So it's like, I don't think I'm understanding what they mean by min product. Kadane's algorithm. I have heard of this. Oh, wait, dude. I feel like I do remember something like this. Hey, Big A, relax. Stop it. Relax. You're doing too much. Does he even use a caching approach? Max, relax. Damn. This is not even a cache. That's what I thought. I was like, wait, interesting. Wow. Is it? I mean, I genuinely I don't understand. Like, there's no DP involved in this. Is there? I mean, maybe it's doing a bottom approach, but like, okay, so it's wrong. Well, then let me control Z real quick. Oh crap! Because it's a multiplication operation. Son of a gun. I don't know. Now I'm stumped. Yeah, I had a feeling that's probably not gonna work. Well, wait, What? Wait, why? Am I tripping on this? Why am I tripping on this one? You're pissing me off, motherfucker. Oh, crap. I see. I'm tripping. Never mind. I don't know. What qualifies as the min product, though? We'll see. We'll just try one more thing. We'll see. I have no idea. These questions are so upsetting, brother. What's up, man? I mean, it's a little silly, but I don't know. I highly doubt this will work. What? No, this I mean, that worked like... What? What? I'm so confused. I don't even know why that works.
Hey everyone, welcome back, and let's write some more neat code today. Let's look at maximum product subarray. And this is actually a dynamic programming problem, and I'm going to show you how to solve this problem easily. So we're given an integer array of numbers, and we want to find the contiguous subarray that contains at least one number and has the largest product. So in this case, we have a 2, a 3, a -2, and a 4, and the largest continuous product we can make is 2 and 3, because 2 times 3 is 6. That is the largest product. We can't really make it bigger because there's a -2. If we multiply this by -2, it's going to be -12. That's not bigger than 6. So what's like your first idea how to solve this problem? Maybe brute force, right? Is there a brute force solution to this? Well, we want to find a subarray, right? So why don't we just try every single subarray? So let's say all subarrays starting at 2. We got 1 subarray, 2 subarrays, 3, 4, right? And for each of these, let's just calculate the product, right? Like the first one is 2, the next one is 2 times 3, the next one is 2 times 3 times -2, the last one is 2 times 3 times -2 times 4. And we end up saying that so far the biggest is this, but we're technically not done yet. All of these subarrays contain 2. So now let's look at all subarrays containing 3. So we got 1, right? Just 3. Then we got 3 times -2. Then we got 3 times -2 times 4. And basically we repeat this process. Now you can tell maybe there's some patterns to this problem that we can use to our advantage to find a better solution than n squared. So let's look at one example. Do you notice anything about this subarray? Well, all elements are positive. So what does that end up doing? Like this is all positive. So we got a 1, okay? And next we want to check this subarray, okay, multiply it by 2. We want to go even farther, check the 3, okay, multiply by 3. And what if we kept having positive elements? 4, 5, multiply by 4, multiply by 5. Do you notice something? Up until this point, our product is going to be a 1. Up until this point, it's going to be a 2. Up until this point, it's going to be a 6. Up until this point, it's going to be a 24. Up until this point, it's going to be 120. If we have positive numbers, no matter what happens, they're going to keep increasing, right? So this is the simple case. If we get all positive numbers, then our product is always going to be increasing. So now let's actually look at the opposite scenario. What if we had all negative numbers? Because all positives is easy. You just multiply all of them, you get the max product. But with negative numbers, it's a lot more tricky. So let's look at the first number. So up until here, the max product is just -1. And then we add a second element, a -2. And then what do we get? We get -1 times -2. And we know that the product of that is 2, right? Positive 2. Now the last subarray we checked from all the way from -1 to -3. So we introduce one more value, a -3. And now if we multiply all 3 of these numbers together, we see that our product actually got smaller. Now it's -6. And what's going to happen if we had another element over here? What if we had a -4? Then we multiply by -4, and now we see that our product is going to be 24. So you see that when you have negatives consecutively, the sign is alternating. So when you want the maximum, it makes it kind of tricky to have negatives. But we also see that even though we got a -6 over here, there's actually a subarray that has a better solution. If you just take these two numbers, -2 times -3, we get a +6. So why did we get a -6 over here? How can we find the real maximum, which is +6? So even though we're looking for the max product subarray, we're actually also going to need to keep track of the minimum as well. And I'm going to show you why. So first, do you at least agree with me that if we want to find the max product array subarray of this, of the entire thing, it might be helpful for us to at least solve the sub problem, which is the max product subarray of just the first 2 elements first, and then use that to get the entire one. Okay, that makes sense. We know that the max product subarray of this is 2. Now, if we had a positive 3 over here, then we would say, okay, if I can get the max subarray of the first 2 elements and multiply it by 3, I'm going to get 2 times 3. It works when these are positive numbers, but we actually have a negative 3 over here. So I'm going to say, get the max product subarray, which is positive 2, but let's also get the minimum product subarray of these 2 as well. And what do we know about the minimum? What's the minimum product subarray of these 2? It's going to be negative 2. So I'm going to keep track of both positive and negative. So we have a positive 2 and a negative 2. We keep the max and we keep the minimum. So now when we want to compute the max product subarray, when we include this 3, then we can compute that. We can compute that using both of these values. So we know that when we take the maximum, 2, we get negative 3 times 2, which is negative 6. And we know when we take the minimum, we get negative 3 times negative 2, and that gives us a result of positive 6. So we know the maximum is positive 6, and the minimum is negative 6. So we take positive 6 and put it over here, and we can take negative 6 and put it over here. And hypothetically, maybe we get another element, and this time, whether it's positive or negative, right? So in this case, let's say it's negative 4, we will be able to find a solution because the minimum, or rather, we're looking for the max product subarray, and we know if we take negative 4, multiply it by the current minimum, which is a negative number, negative 6, we will end up getting 24, which is what we're looking for. But if you reverse it, what if we had a positive 4 here instead? Well, in that case, we can say, okay, positive 4 multiplied by our maximum, right? Our maximum, which is positive 6. So 4 times positive 6, we get 24. We still get it, right? So this, if we maintain the maximum and the minimum, we have all the information we need as we continue to add more elements to our array. So now let's just look at one edge case. So we're talking about positive numbers and negative numbers, but we know that one last edge case exists, the dreaded 0 value, right? So what if we had a 0 value and then maybe some other numbers, 3, 5? Our 0 is going to kind of kill us, right? It's going to kill our streak. Like, look what's going to happen to our min and max. If we take 6 multiplied by 0, we get 0. If we take negative 6 multiplied by 0, we get 0 again, right? X times 0 equals 0. And then if we try taking this 0 and making it a product of maybe 3 and 5, it's going to continue being 0, right? Because any number times 0 is going to be 0. So I'm going to decide to handle this in a different way. So anytime we get a 0 value, I'm going to reset our max to 0, or rather to 1. And I'm also going to reset our minimum to 1. And the reason I'm going to do this is because I don't want to kill our product, right? I'm just going to say that zeros are ignored. We don't really care about zeros. And the reason I'm setting this to 1 is because then when we start introducing new values like 3, it's just going to be 1 times 3, right? Which is going to end up being 3. So 1 is like a neutral value for us. So those are the main things. We want to maintain the max and minimum of our product, and we want to handle the 0 case by resetting everything to a neutral value like 1. Okay, so now let's code it out. I'm going to say our result is initially...
I don't know exactly if this is correct. I mean, there's 190 test cases, but I feel like I could write up a test case that could make this wrong. I don't know. Yeah, I don't know. Well, I mean, it's done, I guess. That problem confused the hell out of me, not gonna lie. We're getting to the difficult ones. We're getting to the challenging ones. Oh, I remember doing this before. Crap. Cat sand would work. Cats and would work. But cats and dog would not work. Part where I get kind of confused is where's the TP, the caching? That's what last time I didn't cache or anything. We only need to cache on bottom or top down. So my choices are, I have two choices. I. What's up, bro? I take a letter and I add it, so I continue like making I continue creating a word, and then if I have a word that matches inside the dictionary, I can take it or I can keep taking a letter and adding it. For my two solutions. Still, I don't. I'm trying to see the caching here. But I'm not seeing it yet. I hate DP. I mean, I love it, but I also hate it. 2D DP is gonna break me. I mean that's what I'm gonna be doing probably tomorrow's 2D DP. I'm gonna hate it. I'm gonna hate it so much. God, I'm not looking forward to that one. 2D DP was actually probably the hardest part of my algorithms class, and I don't remember much. I just remember the hotels problem slightly. So we'll see. Probably do that one again. Max, relax. God damn it. The thing about the caching is like it's different at each point. Like, how can I build upon the cache? I don't know. I'm gonna go no cache to start off with. I don't know. I actually genuinely I just don't know how I'm gonna use a cache in this. Oh my days. Sorry about that. Alright, well. We'll see how this works. I hate these problems. These are actually, like, pissing me off. Like, seriously are pissing me off. Oh, I see. Damn it! I really thought I had it there. Okay. Code. We add it. Oh. Uh-huh. Found the culprit there. This is interesting. Where's the DP though? I mean, like, genuinely speaking, I don't know. Is this DP just like in their terminology, just basically saying like, hey, this is backtracking, but with just a couple extra steps, because this is just backtracking. Okay, so I do need DP. I do need DP. I don't get it though. Like, it's like, where do I use DP? Because like, I could have a situation. Do I have to do like the Cadane's algorithm again, the min max bull? Like, bruh, I don't want to do that algorithm. The algorithm was so annoying. Whoops. Damn. I guess. I don't know. I guess. I mean, whatever. Sure. We'll see. Maybe I'm just a silly Billy, I guess. I don't even know. I genuinely, I don't even know. I don't even know what the edge case would be. Alright, I mean, sure. Hey, works. Let's see if it runs. Nope. Who would have known? Just this is great. I mean, it's a good test case because they have to do this anyways to see if like you're catching it. But just like, could they have not named it something like actually readable? You know. See, the issue is my caching is basically going on the first round saying that, hey, this is impossible. But it's not checking on the second round. The second round, it could be possible. I guess this is where the for loop comes in, right? Dude, I don't even know. This problem pisses me off. Holy shit. Holy hell. I'm so confused. I would honestly take 45 out of 47 and be like, hey, that's not a bad deal. But, unfortunately, it's not correct. Hell. Hey. What are you looking for, man? There's no food. What the hell's your problem? Base condition is to return true if we reach the end of the strings. Is that not what I'm doing, but just like a smarter approach with the for loop? Because I'm still confused of what the hell we're caching, man. I mean, genuinely, I think if I figure out what we're caching, like we'll be in a better situation. But like, I have no clue, man. I have no clue. It works for a little bit, but it obviously, like, I don't know. Who knows? Maybe my cache is correct. Maybe it's the DP part that I'm fragging out on right now. I don't know. Yeah, no clue. We'll do bottom up ish. You know, I'm not the biggest fan, but I guess you gotta do what you gotta do. I don't know. Okay. Actually, don't even need that. Is that gonna run? Runtime error. Right. No, it's not gonna run. God damn it. That worked. Alright, run it. See what we get. It's gonna give us a timeout error. You know, no surprise there. I'm not great at caching bottom up. Oh, it's not a timeout error. Nope, it is a timeout error. Okay. Okay. Hey. Oops. I'm guessing it's gonna fail on 45 again, or it's gonna time limit exceeded. I mean, genuinely speaking, like I don't know what I'm expecting here, because like this is the fun part about like bottom up. The question I have is how many times is this going to run? Based off of how my thing should work, if it works, which obviously it's not, there should not be any repeated digits. Oh boy. Well, that's not the problem here. Oh, yes it is. What the hell? Repeating digits? Why, brother? Why? Oh, wait. Sorry about that. Of course it's repeating digits. I'm just, being silly. Okay, here you go. It is repeating. What? What? Maybe I'm doing bottom up wrong. You feel me? I gotta switch back down to my top down. I'm just not. I'm not a bottom up kind of person. I never get it right. I genuinely, I never get it right. I always mess it up. It just, to me, top down, it just makes more sense. I don't know. I guess crucify me about that. I know a lot of people, they love their bottom up. I always mess it up. Like, realistically speaking, no, you know. Alright, let's try that. I don't know if that's a proper augmentation. Nope, it is definitely not. Fuck. Ah! Oh my god. Oh, fuck. Oh! Yes. Alright, still doesn't work. Ah! Damn, man. Oh, come on. Again? We're not caching right now. What's going on? Jesus. Here it is. This is the type of shit that be pissing me off. I don't know. You gotta. I can't tell.
Hey everyone, welcome back, and let's write some more neat code today. Today let's solve the problem word break. So we're given an input string and a dictionary of strings called wordDict, and we want to return true given an input string LeetCode, and we're given a word dictionary of, right? So let's try maybe the first two characters. So instead of starting from the first position in the string, we would start n. Now, we could also do it a different way. Instead of trying every single possible, prefix, let's just check every word in our word dictionary and see if that matches. For example, this first word is 4 characters long, right? So what we're going to do is we're going to check the first 4 characters in our string. Does this match this word? Clearly it does, right? So what does that tell us? That tells us now, we have the same subproblem as before. We're going to start from this next position now, right? And check. And from here, we're basically going to be doing the same thing, right? So we're going to check is leet, basically, the first 4 characters, does that match leet? This does not match leet, right? So now let's check the next word in our word dictionary and check does that match the characters over here. It does, right? We found code. So this is basically another way to do this problem. Instead of checking every single possible prefix, right, of any length, what we're going to be doing is we're going to be checking every single word in our word dictionary as the prefix. So instead of being O of n times n, we're going to be doing O of n because potentially we are going to be going through every single starting position, but we're going to be multiplying by the number of words in our word dictionary, which is, let's call it multiplied by m. So I'm just going to basically show you the same formula that I usually do. I'm going to give you a quick illustration of what the decision tree would look like. Then we're going to understand how we could cache that to eliminate repeated work. And then by understanding that, we're going to go to the optimal dynamic programming solution, the bottom-up approach, and then we're going to code that up. Usually the DP solution is a lot less code than caching. So we're going to be looking at our input string neat code. So I think that's a little bit better than neat code, wouldn't you say? So what the decision tree is going to be is we're going to start at the first position, right? For example, I equals 0. We're going to be keeping track of whatever index we're at, right? Because we know that if we can find a word, that matches neat, for example, then the subproblem is going to be, finding words that can match the remainder of the string. For example, if we did that, our I, instead of starting at index 0, would basically be starting at index 4, right? So that's what the subproblem is going to be. So really, we're only going to have one variable that we're keeping track of in this backtracking solution. And so remember, we mentioned we're not going to be doing it like this. We're not going to check every single prefix. We're going to have decisions in our decision tree based on the number of words that are in the word dictionary. So we're going to have a decision for neat, we're going to have a decision for leet, and we're going to have a decision for code. Now, what we're going to notice is when we try leet on here, right? Basically, leet is 4 characters. Therefore, we're going to check the first 4 characters of here, compare it. Does that match leet? It does not, right? We're just 1 character off, that first one. So basically, that means we're not going to continue down this path. Now let's try code. Does code match the first 4 characters? Definitely not. So we're not even going to continue down this path either. Of course, neat does match this. So we are going to continue down here. We're going to do 3 more decisions, basically 1 for every single word in our word dictionary. Now, one thing though is when we are starting here, we know we match the first 4 characters. So by this point, we are now going to be at I equals 4, meaning we're going to be looking at this part of the string. So as we can see, checking neat, that's 4 characters long. So let's check 4 characters starting from here. That's not matching, of course. So then we're not going to continue here. Leet, does that match over here? Nope. We're not going to continue down this path. Code, does code match this portion? Yes, it exactly matches. So therefore, we're going to update our I pointer again. Since we matched 4 more characters, we're just going to take I and add 4
4 to it now. So now I is going to be at 8, and 8 happens to be that exact position right after the end of the string, right? This is where index 8 is. Therefore, we basically know that we were able to match the entire string. Therefore, we know we can return true, right? Once we find a single true, that means we just terminate, we end the function, we can just return true, and the function is done. Now, from this example, it might not be super intuitive why we would use a cache, but let's say we had another path in our decision tree that led us to, for example, index I equals 5, right? And let's say we use all 3 decisions in that path, and let's say none of them yielded the correct result, meaning we were not able to word break this string from starting at index 5. So then we would return false from this path, right? And we would want to cache that. We would want to say that, let's say dp of index 5, right? We would want to set that to false. Basically, what we're saying is if we ever reached this same function call, if we ever tried it again, maybe, this decision tree could be really big. Maybe there would be another path from, somewhere over here where we tried index I equals 5 again. In that case, we would want to return false immediately because we saw from here there was no possible way to break it down. Therefore, we don't need to redo all of that work if we, try the same exact thing. So we discuss.
Genuinely, I don't see where my stuff is breaking. I don't know, man. I don't know. I'm feeling very defeated. You go from graphs, you get cooked. You start doing DP, you get cooked. You get to the end of the leak code ground, when you start getting to the more complex things. It's like, brother, take me back to 2-pointers. Holy fuck. Oh. Wait a minute. Hold up. Wait. Dude, am I trolling myself? Hold up. I actually think I'm trolling. I think I'm trolling. If you're watching this video and you're sitting there and you're palming your face right now because I just pulled the stupidest move ever, I don't blame you. I don't blame you. I mean, this might not be it. Hey. This might not be it. I don't know. Come on, what the? Oh. All right. Come on. Kill it, kill it, kill it. Thank you. Dude, I'm such a fucking idiot. I literally had it, bro. Oh, yeah. Alright, man, whatever. I'm gonna count that as a win. I don't care. That was a win. That was a win. Cause I literally, I did have it. Alright. Okay, it's just, it wasn't really me being the smartest of smarts. Not big guy. Alright, longest increasing subsequence. See, sorry, check this one real quick. What's up? Stop it! Relax, relax. Max, chill out, brother. Dang. Look at you, man. You hate it when I make my videos. I'll be sitting in this chair coding, like being quiet. He don't care. I don't go fuck. The second I start talking in the mic, he gets pissed. He wants attention. Bad. You feel? I think he's got FOMO. I think he's got fear of missing out. Or maybe he thinks I'm going insane as I'm talking to a wall. You think I'm going insane, buddy? Probably. Alright. So this uses the, this is the same algorithm that's used for the diff algorithm, which is something that I need to study actually for my fall internship coming up, if I still have it. These budget cuts are killing me, man. I don't remember how I did this. This isn't a sliding window approach, is it? 1, 1, 1, 2. Three. No. It's not a sliding window approach. Crap, man. Fuck, what do I do? I'm trying to think of my decision tree here. I can either take it or ignore and move on. Alright, let's draw out my decision tree. So I'm at 10. And then I see that 9, so I can either take it or I can leave it, so I can... Or maybe we'll only... Okay. We'll take it, it's increasing. Okay, so I see a 5. Alright, so then I can branch off. I don't see this going right. I'm gonna have to move this. Crazy. Even like, look how far that is, and boom, whatever. Or you know what I can do? I can do this. What? Whatever. It's fine. It's fine. It's not a big deal. They'll be tweaking over nothing. Okay. There we are. Huge tree now. Okay, so then we get to the last one, we get to 18. So, with 18 we can go to 18. Or 2. This one we can just go 18. Or itself, you know. 2, 7, 18. Right? 2, 3, 18. 2, 3, 7, 18. 3, 18. 3, 7, 18. Right? And then it's the biggest we can go. Ow, 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 ow. Ow. Alright, sorry. Just thinking about my decision tree here. Uh, okay. We're going to do a take and skip operation. We're going to do bottom up DP approach. I'll try it at least. We'll see. Or current -1 is less than or equal to index. Then we're going to do a there you go. We can take if it's this way. Sorry. Okay, let's take. This is if we take or not. Just don't take, and there's probably a third option, which is just reset, right? And then there's reset, which is going to be a DP of index +1, and then nums of index. Okay. So we'll do that. It's all these arrays. Fuck! Oh, this could be bad. Crap. Whatever, we'll do that. This is like chopped. This is no way. This is how you do it. Ah! Oh, man. I think I wrote it wrong. Did I? This is honestly like too confusing. My brain is like, fuck. Oh, dude, my brain is not cooperating with this at all. Pissing me off, brother. It's pissing me off. Whatever, man. Whatever, brother, man. It's gonna be a big fat nothing. Big fat nothing. Oh, did I do S? It's numbs, bro. No. Okay, we're actually chilling. Thank you. No, we're not. Dude, I hate this problem, man. The problem blew up. It's too much going on. It's not even. I'm not even looking at it as a feasible possibility anymore. It's I don't know. Five hints. Jesus Christ. Oh, wait. Hold up. I'm trolling. Okay, if index not in cache, then we're gonna do include equals exclude equals we just do previous, right? I can always do exclude. See, the problem is this automatically assumes that the first one is in the order. Not gonna happen, brother. Not gonna happen, man. This ain't gonna work. No. I can't do that. It's not gonna work. I'm just gonna call it array. Dude, I hate this shit. Like, genuinely, honestly, genuinely, bottom of my heart, I hate this stuff. It's so aggravating. Whatever. Whatever. I mean, it's fine. It's whatever it means. Okay, you gotta hurry up because I gotta go to bed soon. I don't know. I mean, I'm blanking right now. Respectfully, I'm out of it, man. I'm out of it. I don't know. Zero? Like, dude, whatever. I'm so confused. Genuinely so confused, man. Yeah, print array. And 101 low. How? I mean, how is that the only one we come to a conclusion on? None of the other ones? We didn't come to any conclusions on none of the other ones. I mean, genuinely, how? We have to, there's gotta be like multiple. Okay, here we go. Now we're talking. Ah, crap. part I hate about caching, bro. It needs to be like, fuck. I'm not caching properly. If my professor could see me, he'd be so embarrassed. I need to go TA algorithms or something like that so that way I can relearn. I don't think me doing top downs is gonna change realistically anything about this predicament I'm in. I think this is just how it's kinda is right now. It sucks, but let's see it. I don't know. I mean, I did it wrong. Anyways, but now I'm confused. Oh, no, I can't. I see exactly what went wrong. I'm tripping. I forget how fast the computer moves. Yeah, wrong answer. Fucking A, man. Genuinely, like, what do you even do in this predicament? Genuinely, like, what do you do? I don't know. I don't know. My cache is not caching the way I envisioned. And even with that process, it still doesn't work. I don't know. I'm so tired. It's been like 2 hours. These problems, they hurt my head. A hash map or a 2D array? So, okay, well, my solution, logic-wise, is perfectly fine, I think. The issue is the caching. I'm not caching it properly. .2D array. I think that might have given at least an idea away. Maybe. We'll do -1. I mean, realistically, I don't even need this MJ. What am I doing? Let's see. I mean, does this have any merit to it? No. What am I missing? I mean, like, what's the cache? I don't know. I don't know. So I mean, it seems like.
Hey everyone, welcome back. Let's solve another problem today, longest increasing subsequence. And this is another tricky dynamic programming problem.
Yeah,
And I'm going to show you how to go from the recursive
Fucking
solution to the dynamic programming solution. So we're given an array of numbers, and we just want to return the length of the longest increase. In this case is 4, so we return 4. So the first idea you might have is brute force every in our in our choices if we want to generate every approach and then somehow modify it to get three elements. But how can we do this with an algorithm that's efficient? Well, let's start out with the brute force approach. Let's check all subsequences starting at index 0 and then repeat that starting at index 1, starting at index 2, and starting at index 3, right? So these are the indices. So we take one decision to start at index 0, we take one decision to start at index 1, one decision to start at index 2, and one decision to start at index 3. So in these cases, these are going to be the subsequences we have so far. So we know index 0 has value 1, index 1 has value 2, index 2 has value 4, index 3 has value 3. So now let's go along the first path. So index
index 0. So we know if we start at index 0, we have 3 values that come after it. So we can try all 3 of these possible decisions. So we can go along index 1, index 2, and index 3. And we see that all 3 are possibly valid because all 3 of these values are greater than 1. So we can continue these subsequences. So we know index 1 has value 2, index 2 has value 4, so we can add a 4. Index 3 has value 3, so we can add a 3 to our subsequence that originally was just 1. So now we took index 0 and index 1. So for here, we only have 2 indices that come after these 2 values. So let's continue our decisions. We see that both 4 and 3 are greater than the last value in our subsequence, which is 2. So we can choose both of these decisions. So if we take index 2, then we can add a 4 to our subsequence.
Wait, sorry. Out of curiosity. This doesn't work, right? Wait, if this doesn't work, then that means my whole solution's fucked up. Okay. I'm not using a single cache thing. Let's see. Else print, cached. Yeah, so okay, so it's not my cache then. Motherfucker, man. It's just however I'm writing this is wrong. Oh, I mean, yeah, okay, I see. I don't know. I don't know. There you go. Now back to 2. Dude, I'm kerfunkled right now. Hey, big guy. Yeah. I think what I want to do is I want to print the array. And I'm just gonna include the array. I need to visualize, like, genuinely what is happening in this problem. Because I can't see what's going on. I'm a little confused. Feel me? I hate TP. Right. I was like, what? I was confused. What are we talking about? Genuinely, what the fuck, man? Exclude, man. Or include. What? Why are we not doing any? Oh my days. Fuck you, man. Fuck you. I'm such a fucking idiot. I'm such a fucking idiot. God damn it, motherfucker. Motherfucker, man. I hate it so much. I hate being... I hate it so much. Oh my god, I'm losing my sanity here, brother. I'm actually losing it. Okay. Alright. Okay. Alrighty. Now let's try. That worked. Oh my fucking god. Memory limit exceeded. Let's see. That's not actually a big surprise. I'm not really surprised on that one. So the issue was trying to do like a 2D array is, you get this. That squared is a fucking huge number. So it's like, hold up. What are you doing? What's up? Wrong answer. I don't know. Alright, brother. Explain to me how we're going to cache
If we
this.
take index 3, we can add a 3 to our... No, there's not any elements, so this subsequence has also reached its limit, so we cannot increase it anymore. But so now, let's focus on this caching part. What kind of repeated work have we eliminated? Well, let's just do this out of order. Instead of doing these first, let me show you what happens if we try to extend the 3 now. We try to get another element, right? We started at index 3, but we know that no values come after index 3, so this one cannot be continued. But what do we know about index 3? If we start at index 3 and we want the longest increasing subsequence, we just get a single 3. So that tells us that LIS starting at index 3 is 1. We don't need to repeat this work. And isn't that what we just learned over here? Even though this subsequence is length 3, we are talking about starting at the 3, and we noticed we could add a 3 to it, right? This was the element that we added, but as soon as we added that 3, we could not increase this subsequence anymore, right? That's what this X tells us. We were only able to add one element.
Oh, hold up. Wait. Wait. No, don't run. Come here. Oh, so the cache shows how much more you can add
We
afterwards.
start at index 3.
Dude, that's smart, but fuck, man. God damn. These algorithms. They're actually frying me right now. Is that right? Hold on. Maybe. Hey, big guy. Well, hold on. How does that work?
3. And that's exactly what this 2 told us as well. If we start at index 2, we can add a 4, but this 3 that comes after it cannot be added. We cannot include that, and there aren't any.
The cache tells you how much you can go afterwards. So, ergo, cache of 0 would just be... Huh. How do I write that? You feel whimsical, buddy? Yeah. Well, hold up, relax, relax. What's up? Why are you looking at me like that? Whoa, hold on, relax. Stop it. Relax. You're so bridled with energy. Come here. Yeah, eye bucket. Let me get that off you.
Any more elements to add. So as soon as we finished this and we found this x, meaning we could not go any lower, we knew that the longest increasing subsequence starting at index 2 is also 1. So therefore, if we start at index 2, we cannot go any lower. We cannot continue this. And we don't even have to attempt to do that. And what about this branch? So if we started at index 1, we would start with the subsequence of 2, right? That's what this tells us. And so now I'm going to repeat. I'm going to do some more stuff, right? I'm going to choose the next indices 2 and 3. But wait a minute. Do I actually have to do that? Because look over here. We started with index 1 and we already did that. So when we started with index 1, we saw we had 2 choices, a 2 or a 3 index, right? We could choose this or we could choose that. We saw both of them ended, right? We could not continue either of them. So if you want the longest increasing subsequence that starts at index 1 over here, no matter what you choose, the subsequence is going to be length 2 either way, right? Because if we start with a 2, then we can add a 4 or we can add a 3, but we cannot add both of them. So we can mark the longest increasing subsequence starting at index 1 to be length 2. So we actually don't even have to go down this path once we already go down here because it's just going to be repeated work. And we also see for these 2 trees that we have not finished yet, once we add a 4, the longest increasing subsequence at index 2, which is where 4 is at, is going to be 1, so we cannot continue this anymore. Similarly, once we add a 3, we know no values come after it. The longest increasing subsequence starting at index 3 is just 1. We cannot increase this anymore. So when we finally, in our depth first search, get back to the root, we're going to see that the longest path is one of these, right? Either that, or of course you could go down this direction, but either way, the longest increasing subsequence starting at index 0 is going to be 3. And so when you look at these 4, right, because these are our subsequences, these are the
Alright, come on. Come on. You're like actually tweaking. Come on. Jesus Christ. Come here. I don't know. He's got like the major zoomies right now. He's not gonna calm down unless I hold him. What's up, buddy? Yeah? Are you happy now? Your FOMO is being cured. Not gonna lie, I hate this. Like, I could be spending my nights. I have the project I want to work on, and I've been wanting to work on. I could be spending my nights every single weekend doing that, or every single day doing that. I mean, I spend like 2 hours, an hour to 2 hours every single day. It's been 40 days, so let's say like on average, I do like an hour and 15 minutes, which is 75 minutes times 40 divided by 16. 50 hours. 50 hours I could already spend on my project, but instead I'm doing this shit. And this shit it's not even useful for the job, it's just for the interview. This whole thing, it's just it's so dumb. I don't I don't I don't like it. Hey, big guy, where you going?
The longest subsequences starting at each index. So now let me show you the dynamic programming solution, and it's actually easier than you might think. So we're gonna start at the last index 3 and then work our way backward. So we know this is kind of the base case, right? No values come after it. So the longest increasing subsequence we can make from here is just gonna be length 1 anyway. So we can say the LIS starting at index 3 is just 1. That's the max length. Now, how do we get the longest increasing subsequence starting at index 2, which is just 1 shifted to the left? Well, one possibility is just 4 by itself, right? So that's one possibility. It could just be 1, or it could be 1 plus the longest increasing subsequence starting at position 3. And what this means is if we take both of these, right, because LIS of 3 is just 1, right, so 3 by itself, but we're only allowed to do this if the value nums at index 2, which we know is 4, is less than nums at index 3, which we know is 3. Is this true? This is not true. So we are not allowed to do this. So normally we would take the max of these two values, but we know that the condition to take the max of this does not satisfy, so we only have one choice, 1. So the LIS of this is going to be 1. I'll put it over here like in the corner. So again, we're going to work our way backwards. So let's get the longest increasing subsequence, 1 index back at index 1. So we're going to do the similar thing that we just did. So we know we could take a subsequence 2 by itself, right? That's one choice. 1 is a choice, length 1. We also have a choice, 1 plus the longest increasing subsequence starting at 4, and we're allowed to do this because 2 is less than 4, so it is increasing. The subsequence is increasing. So another choice is 1 plus LIS of 2, and another choice is LIS starting at index 3 because 2 is less than 3, right? 2 is less than 3, so the subsequence is in increasing order. So 1 plus LIS of 3. Now we know that this is 2 and this is 2, so it doesn't really matter which one we do. The LIS of 1 is going to be equal to 2 regardless. So now we want the longest increasing subsequence starting at index 0, and we're just going to repeat what we just did. So we can take 1 by itself, which is just 1, or we could...
Holy fuck. Okay, actually, I do remember doing that. Dude, that's been forever since I touched that. Holy hell. Oh my god, it's 12:40. Damn! Let a brother breathe. I can't. Let a brother breathe, man, please. I can't do this. Oh, it's gonna kill me. It's gonna kill me. Whatever, man. Okay. What's up, big guy? Got the zoomies again? No, this is gonna create an infinite loop. What am I doing? Dude, this is gonna create an infinite loop. Fuck.
You take 1, add it with the longest increasing subsequence starting at 2, or this longest increasing subsequence starting at this index or this index. So we know we're going to get 1 plus 1 from here. We're going to get 1 plus 1 from here. And we're going to get 1 plus 2 from here. And we're allowed to do all of these because you notice 2 is greater than 1, 4 is greater than 1, and 3 is greater than 1. So they're an increase. So they are in increasing order. So then we know.
I don't know. I'm genuinely like so confused. I'm like right there. I don't want to give up because like I understand. This part that's like upsetting. It's like I see what he's saying, but I'm not able to like code it out. Like that's the part that's problematic right now. What's up, big guy? Infinite loop? Because I'm not incrementing. Of course. God damn it. Yep. No, I see. I understand. Time index. This goes 1, and then index. This goes 1. Or, sorry. This goes 1. Hey! Relax! Hey! Stop it! Stop! What are you doing? No! Jesus Christ. It still doesn't work. Dude, I don't. I'm so fucking tired of this fucking problem, man. Holy hell.
So they are.
Stop. You're gonna get yourself electrocuted. Do not play with the wire, man. Dude, you're being a pain in the butt right now. What are you doing? Relax.
Are in increasing order. So then we know that the long. So let's have a cache or a list. In the example, we're going to start at index I, like this could be I, and then we want to iterate through every subsequence that came after it. So I'm going to have another nested loop for j in range. So starting at I plus 1 and then going to the end of the input array. And before we can update LIS, we want to know is the value at I actually less than the value at...
Oh, crap. Yeah. I forgot about that. I'm still confused as why that passed. I don't know. I don't know. Like, I actually... I don't know. Yeah, plus 1. This hurts me, man. This genuinely hurts me that I'm, like, having to be stuck on this problem for a fucking hour. Let's see.
J, because J comes after it. If we want this to be an increasing subsequence, this condition has to be true, okay? Because we know for sure J is going to be an increasing order with I. And literally that is it. We made sure to evaluate that it's an increasing order. We did it backwards. We made sure to cache the repeated work. What do we have left to do? Well, we want to return what the max is. How can we do that? Well, in Python, you can just take the max of a list. So whatever whatever the greatest value is in here is going to be returned. And there actually, so this is O of n squared, and there actually is a better solution.
Really? Wait, hold on. Huh?
What?
I don't want to do this store. Genuinely speaking, how does that work? I don't even know. I don't even know. I don't know. I mean, we're just cruising through this. Not even cruising. We're having a horrible time. We're actually having a horrific time. There's no cruise. This is just pain and agony at this point. Oh, come on. Don't. Whatever. It's fine. I honestly don't even care anymore. Like, that was ridiculous. We're done. Yeah, I need to come back to that problem another day. Let me start that. Okay. I'm done. Sorry, that video was more painful than it needed to be. That's just dynamic programming for y'all. You know, it's not sunshine and rainbows. It's a little painful, but you gotta do it because you never know if that's the question a company's gonna ask. Alright, well, thank you guys so much for watching, and I will see you tomorrow.